Good day, learners. Welcome to Technical Sciences lesson. My name is Zamisile Mdima. This lesson is brought to you by Sci-Bono Discovery Center in collaboration with Gauteng Department of Education. So today we're going to be looking at sound waves. So this is the second lesson on pulse and waves, as we took a look at the important definitions at the first time. So we're exploring the terminology that is important for this specific chapter. Okay, so what is it that we're going to be focusing today? So we're going to be looking at the relationship between the pitch and the frequency. We're going to be also looking at the relationship between the amplitude and loudness. We're also going to be exploring the type of sound waves that they are, together with their uses in the everyday life. We're also going to be analyzing the long question, okay, so that we have a better understanding of how this question, or rather this chapter, can be asked in an exam. All right, so before we even get started, let's take a look at the lesson objectives. So these are the objective for the lesson, which is what you and I should be comfortable with or should understand by the end of this lesson. Okay, so point number one, I want you and I to be comfortable to be able to define important terms. Remember, on the previous lesson that we had, which was the first lesson on waves, we were able to define important terms so that we have a better understanding. So when we talk in terms of an amplitude, you know what an amplitude is. When you talk in terms of a pulse, you have a better understanding of what a pulse is, and you're able to differentiate it between a pulse and a wave. Okay, so we're going to be continuing with other definitions as we are going to be looking specifically this lesson on sound waves. All right, so point number two, I want you and I to be able to differentiate now between the types of sounds that are there, the different types of sound waves that are there. So you're going to be exploring an infrasound. How is infrasound different from the audible sound, and how is the audible sound different from the ultrasound? Okay, and where exactly do we use these sound waves in our daily lives? All right, third point, I want you and I to be comfortable, to be able rather to understand the relationship between frequency and pitch. Okay, so what happens when I reduce the frequency? What happens to the pitch? What happens when I increase the pitch? What happens to the frequency, and vice versa? All right, and also we're going to be exploring the relationship between amplitude and loudness and how they affect each other. Okay, how can we tell that the sound is too loud or it is too soft? What is it that tells us? Okay, how does the amplitude affect the loudness? In fact, that is going to be what we're going to be exploring. All right, so by the end of this lesson, I want all these points to be able to be covered for us to be able to understand and be able to explore all the relationships highlighted. All right, so let's get to it. On the previous lesson, what is it that we explored? We spoke in terms of a pulse. We described a pulse as a single disturbance that moves through a medium. Okay, just a single pulse moving through a medium. We also said we know that at that point you did not understand what a medium is, so we had to describe what is a medium. All right, a medium is the substance or material which a pulse moves. Okay, so that single disturbance is able to move through a medium. It can be a substance or the material where the pulse is moving. All right, what is important for us to notice or to bear in mind is that the medium just carries the pulse from one place to another. However, it does not create the pulse itself. All right, so we had to give examples of the medium. Okay, we said, okay, what could be examples of the medium in which this single disturbance is able to propagate in? And then we said it is air, it is water, or any solid substance. All right, so sound, or rather sound pulses, are able to move in air, in water, or a solid substance. All right, and then we said, no, there's not only one type of pulse, but there are two types of pulses. So now we need to be able to differentiate between these two. All right, we said let's explore each, okay, and understand it in deeper detail, then move on to the second type. The first one we spoke about is the transverse pulse. We said, okay, for us to be able to understand how a transverse pulse behave, we have to be able to define it fully. And from that definition, we are able to then understand the particles in it and how they are moving. Right? We defined a transverse pulse as a pulse in which the particles of the medium vibrate at right angle to the direction of propagation of the wave. All right? So that is perpendicular to each other. You find that this is the direction of the propagation of the wave, and the particles of the what? Of the medium are vibrating at right angle, creating that 90 degrees angle. All right. So this is a what? It's a transverse pulse. So not only is there a transverse pulse only, but there is also a longitudinal pulse. Okay, then how is it different from that other one? So this one, a longitudinal pulse, is a pulse through which the particles of the medium, they are vibrating parallel to the direction of the propagation of the wave. The propagation of the pulse, because we're still talking about the pulse at this time, just the single disturbance. All right, so you find that your pulse is propagating in this direction. Also, the particles of the medium are vibrating, okay, in that direction as well. So you see, it creates a parallel relationship between what? The particles that makes up the medium, as well as the what? The direction of the propagation of the pulse. All right. So pulse is a single disturbance. It is able to move through a medium. A medium could be air, could be water, could be a solid substance. Okay, the medium does not create a pulse, but it just allows for this pulse to move from one position to another position. Okay, there are two types of pulse: a transverse pulse as well as a longitudinal pulse. Right, so this is what we learned from the previous lesson, and we have to remind ourselves of what we had learned so that we better incorporate it with today's lesson. Right, then we moved right along. We spoke about a wave now, and then we said we need to know how a pulse is different from a wave. Okay, we said a wave is a periodic continuous disturbance, no longer a single disturbance that moves through a medium. However, a continuous disturbance, okay, that consists of a train now. There's repetitiveness, okay? So this single disturbance is being repeated, okay, numerous times, because now we call it what? A continuous disturbance, okay, that consists of a train or successive pulses, all right? Again, we had to explore the types of waves now. Okay, how many waves are there? Now that we know what is a wave, there's a transverse wave again, and there's a longitudinal wave again. All right, so now a transverse wave, we defined it as a wave in which the particles of the medium, they're vibrating at a right angle to the direction of the propagation of the wave. Okay, now we're no longer talking in terms of a pulse. It is a wave because it's continuous. It's a continuous disturbance that consists of a train or repetitive or succession of pulses. All right, but not only is that, right, let's just go back a little bit. We have to explore, okay, the parts that makes up a transverse wave. Okay, we said we're going to look at this one by one and in detail so that we are able, so if somebody comes to you and asks you in terms of an amplitude 1, you are able to point it out in a transverse wave, and 2, you are able to define it fully because you know where it is positioned in a transverse wave. All right, so we had to look in terms of a diagrammatic representation of how a transverse wave would look like. All right, we said this is an amplitude, okay, and that is the crest, right, and that is the trough. We said for us to be able to remind it easily, so when we say we call it, we're naming the alphabet A, B, C, C comes first, okay, C that makes, or that is there, and then the word crest comes first, and then for T, which is trough, is right there by the end closer to the Z. All right, so what does that mean? It reminds you that C is at the top. That means that the crest is at the top, and then the trough is at the bottom. All right, both whether you're talking in terms of the crest or you're talking in terms of the trough, there's always going to be an amplitude. Because what is amplitude? Amplitude is the maximum displacement from the rest position. Okay, so the maximum, the fact that you're coming from the rest position to the highest point of the crest, and from the rest position to the highest point of the trough. Okay, so that is why we defined the amplitude as the maximum displacement from the rest position. So in some books, they will call the rest position an equilibrium point, which is one and the same thing. It is still fine. Hence, over here, it is written equilibrium or the rest position. Okay. Then we explored the wavelength. We like a wavelength is the distance between the points that are in phase, okay, or the crest that are in phase. Can you see that the wavelength is between the what? The crest in this case that are in phase. Here is a crest, here is another crest, okay? And they are in phase because they are in the same state of vibration, all right? Another wavelength will be moving from over here to over here, okay? This is still your what? Your wavelength, okay? Wavelength is also called lambda. It's a Greek term, all right? And we have to use the SI unit of what? Of meters when we talk in terms of the wavelength. So you might be given in different SI units. It could be millimeters, it could be centimeters, could be kilometers, sorry. So we need to be able to move from any other SI unit that we're given to the appropriate one of what? Of meters. Okay, so that means conversions come in there. They are very important for us to take note of. All right, so that is the wavelength, as we did mention. Just to remind ourselves a little bit of the conversion that we just spoke about from the grade 10 content. It is kilometers. I'm just going to write it in the simplest form ever, and then meters, and then centimeters, and then millimeters. Okay, right. My millimeters are not seen right. And then from kilometers to meters, okay, that means we have, because now we're moving from the bigger SI unit to the smaller SI unit, we have to times it by what? By 1,000, because kilo means 1,000. And then from meter to centimeter, we need to times it by 100. And then from centimeter to millimeter now, we're timesing it by 10, okay? Then we go back. Hence, my arrows are going to the original direction I started in. Okay, now we have millimeter. We're moving from millimeter. We're going to the centimeter. Okay, so from millimeter to centimeter, we divide this time, okay, by the same factor. We would use the factor of 10, but in this case, because we are moving from a smaller SI unit to a bigger SI unit, we divide by 10. All right, so and then from centimeter to meters, all right, we divide by the same factor, which is in this case 100. Okay, and then from meter to kilometer, all right, because now we are moving from a smaller SI unit to the bigger SI unit, we are dividing by 1,000. All right, so in cases whereby you find that you are given a value or a number in millimeters, you look at where you come from, and then you want to go to meters because that is an ideal SI unit for what? For the wavelength. So you look at where you come from. This is where I'm coming from, because you would have been given something in millimeters, and then you want to go to meters. Okay, can you see where I am? Right. And then you say, okay, I need to divide because I'm moving in this direction, right? That is clear. But what factor am I going to divide by? So I'm going to divide by 1,000. And what informs us of that? You count the number of zeros that you jumped. So you jumped 1, 2, and 3. So that means you're dividing by 1,000. All right. So if in cases whereby you had to move from a kilometer and then you're moving to a meter, okay, in which direction are you taking? You're taking the right direction. That means that you need to do what? To multiply, right? And then by what factor? By 1,000, because you're moving from a kilometer to what? To a meter. So in every corner that you would have been given a number in, you need to be able to move your way to what? To the meters, okay? So this is the easiest way of looking at it. And then number 2, we have a different type of the wave. This is a longitudinal wave. What type of a wave is that? It is a wave in which its particles that makes up the medium, they move parallel to the direction of the propagation of the wave. The everyday example is the spring. Okay, so here's the direction of the motion of the wave, okay, and then the direction of the motion of the particles that makes up a spring. Okay, so hence they're creating that parallel relationship between the motion of the wave and the motion of the particles that makes up what? A spring. Okay, how best do we then represent the longitudinal wave? Okay, we represent it using the lines. The closer they are together, sometimes they are closer to each other, sometimes they are far apart to each other. All right, so what do we then refer these when the lines are closer to each other? We refer them to as what? The compression. And then when they are far apart from each other, we refer to them as what? As the rarefaction. Okay, so still on the same one like this one, we still do have a wavelength, which will be in between the what? The successive compression or the successive rarefaction. Okay, so for example, this one, this rarefaction over here and this rarefaction over here is the what? The wavelength. Okay, this compression over here and this compression over here is what? It's a wavelength, and it has to be in meters. Okay, so given a distance, you need to be able to see how many wavelengths are there, okay, so that you are able to take just the wavelength that you need. Okay, because sometimes they give you a distance that incorporates many waves. Remember, in a transverse wave, you need to have, for a full wave, okay, to be complete, you need to have a crest as well as the trough, right? That is one full wave. Okay, so in terms of the longitudinal wave, you need to have a compression, you need to have a rarefaction. That is a complete wave. Okay, a compression, a rarefaction, and so on. Right, so we're reminding ourselves of what we spoke about the last time before we get into today's lesson. Right, amplitude, we've already defined it. This is the maximum displacement from the rest position. It could be in the crest, it could be in the trough. Okay, as long as the starting point is the rest position, or rather you call it your equilibrium position. Okay, that is your amplitude. And how can you just point it? This is the amplitude. Okay, this is the amplitude over here. All right, so what else did we talk about? We did talk about the wavelength, which is the distance between the two successive points, okay, that are in phase. They have to be in phase. And how can you see that they are in phase? This has the same state of vibration as that one. All right, so this is the successive crest, and this is the successive what? Trough. Okay, meaning that they need to follow. When we say successive, they need to follow each other. It could be here and here, not jumping a certain trough and then on the other one. So they have to be successive. They need to be closer to one another. All right, that will give us what? A wavelength. All right, so also mention that the distance between the two adjacent crests is the same no matter which two other adjacent crests you choose. Okay, so you can choose the first two or you can choose the last two. That is still fine. It will have the same distance, okay, between the two adjacent crests or between the two adjacent crests, trough, that is. SI unit for the wavelength is important. Why is it important? Because when we are asked to calculate the wavelength and it's not given to us, we should be able to write the answer in correct SI units. Okay, so SI unit for wavelength always has to be in meters, and we've spoken about the conversions. Okay, so now you know how to then move from a given SI unit. It doesn't matter which one. Okay, move your way to the what? To the meters. Okay, because that is very important. And I kept mentioning something about the points in phase. So what is a point? What kind of points are they when we say these points are in phase? The points that are in phase, it means that the 2 points that are in phase have got the same state of vibration. Okay, they are vibrating in the same state. Okay, so let's look at these examples. So we have a P. Let's start with the P. So can you see P is vibrating at the top of what? Of the crest. So for another point to be in phase with P, it has to vibrate just at the top of what? Of the crest. Hence we look at P1 and we look at what? At P2. So if there was a point over here, it will vibrate where? In the same position as P. Let's look at another one. Let's look at R. R is right at the bottom, is right at the trough. Okay, so we look at R, it is vibrating at the bottom. All right, and then what other points are vibrating in the same state as R? Okay, it is R1 and also it is R2. All right, so that's what we look at when we talk in terms of the points that are in phase. Okay, the other ones that we can look at is Q, as well as Q1, as well as Q2 are vibrating in the same state. Okay, so these are the points that are in phase. Okay, now let's look at the ones that are out of phase. Okay, that means that it's the opposite of the points that are in phase. So what's happening on these ones? It means that the 2 points are out of phase when they are not in the same state of vibration. Let's take it the obvious one. Just want the obvious one. You're looking at B and then you're looking at D. The other one is at the trough. The other one is at the crest. The other one is at the trough. The other one is at the top. The other one is at the bottom. So these are not in the same state of vibration. All right. So they are definitely out of phase. All right. So I made a few examples so that it is easier for you to see. So C is out of phase with A. Definitely out of phase because it's in a different state of vibration. Okay. So C would have been in the same state of vibration as what? As a point that could be here. Okay, so and then we have, let's just name it. So if this is EFG, let's name this as what? As H. Okay, so this would have been in phase with G. All right, so C and G would have been in phase. Okay, however, C is definitely out of phase with what? With A. Okay. So look at another example. Point D is out of phase with B. Where is B? Definitely out of phase, right? And then we look at the other ones that are in phase now. E, they say E is in phase with A. Correct. Okay. And then in phase with B, that means F is in phase with B. Very correct. Okay. So that's how easy it is to spot, meaning that every time when you are asked a question about giving a pair, okay, of the points that are in phase and out of phase, you need to really give a pair, meaning that you cannot just say F is in phase, that's it. With what? With which other point? So you need to give an answer in pairs all the time, because now there is a comparison between which point and which point are you comparing, so that we look at those points and we see if they are in the same state of vibration or not. Okay. What else did we talk about? We talk about frequency. What is frequency? We defined it as the number of waves per second. All right, the number of waves per second. Okay, and they're given in hertz. We also explored on the formula for calculating frequency, and that is frequency, and this is just a number 1, and this is period. Okay, diagrammatic representation are always good so that we know, okay, and just can be able to see what is it that we spoke about can also be drawn diagrammatically. All right, so this is frequency. As you can see, the first diagram has got high frequency because now it's got an increased number of waves as compared to the other diagram at the bottom. All right, so we say the diagram at the bottom has got low frequency because we're looking at the what? At the number of waves per second. Okay, so if now we had to know how many waves are they in a second in these two diagrammatic representation, let's start counting. Now on the first one is going to be 1, and I'm saying 1 because now for a full wave it has to have a crest as well as what? As the trough. All right. So that is just one wave. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so it's 10. So let's count clearly. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so we've got 11 waves over here. Right, and then let's count on this one. So we get 1, 2, 3. Okay, and then if we were to combine this top part and this lower part, it's going to give us a wave, which is 4 waves. Okay, so the other one, the first diagram, has got a high frequency because there's an increased number of waves in a second. All right, as compared to the low frequency, which got a few waves per second. Why? Because we had to count the full waves. All right. Also, I love this diagram because now it shows us the correlation, or rather the relationship between frequency and wavelength. Okay, that means the higher the frequency, okay, the shorter the wavelength. Okay, because now you can see the wavelength is just short. And then the lower the frequency, the longer the wavelength. Nicely done. Not only did we talk about frequency, but we also explored period. Definitions are important. Once you are able to define fully, then you are able to calculate, you are able to spot the correct formula, you are able to use the correct SI unit. So that means that from the definition, you are able to get all the calculations correctly because you have a fuller understanding of what it is that you are doing. Okay, period, defined it as the time taken to complete one full wave. Okay, we had said that the SI unit for period is seconds because it is the time that you take to complete one full wave. All right. Okay, so we said period is calculated then as this T, capital letter T, is the period. Okay, this is what the frequency. All right, we also explored the wave speed, okay, which is the distance traveled by the wave in 1 second. Okay, so it has to say V is equal to distance traveled over time. This has to be, the distance has to be in meters, and then time has to be in seconds. And this, or you could use this formula of the wavelength over period, okay? Or you can use velocity is equals to frequency multiplied by wavelength. Okay, so on this formula for calculating wave speeds, there are 3 different types of them, simply because it depends on what is given to you, what variables were given to you. Then you are able to use those ones to find the unknown variable. Okay. Now, those were the terms we looked at the last time. It was just a terminology lesson where we needed to just know these definitions, also to be able to spot it diagrammatically, so in terms of what exactly we were talking about. Today, we're speaking in terms of sound wave. We're making sound, okay? But now there are different types of sound, because everything sounds different. A piano sounds different from a guitar sounds different from the drum sounds different from the plates. Okay, the plates sound different from the dog, the barking of the dog. So let's explore now the sound waves in detail. All right, so sound waves need something to travel on, and we already know what a medium is. Okay, a medium, examples of the medium could be air, could be water, could be any solid substance. All right, so sound wave needs something to travel through. Remember, we had said that the medium does not create the waves, it just allows the wave to move from one point to another point. Okay, so there are 3 types of medium through which the sound travels. They are called solid, liquid, as well as what? As gas. So usually they travel through air, but they can travel faster and further through a string. All right. Sound wave is a mechanical wave. Okay, that means that, what does it mean? It's a mechanical wave. It needs a medium. It needs something to travel through. Okay, it is not capable of traveling in a vacuum. So a vacuum, it's an empty space with nothing, absolutely nothing. There is no gas. There's nothing. There is nothing. So you try to speak. Okay, before I even make an example of that, imagine a room. Okay, you take out everything, you suck out all the gas or the air in it. All right, there's just absolutely nothing, and you try to scream in that room, like there won't be any sound that is generated, simply because sound requires air for it to be able to propagate, for another person to be able to hear you. There has to be a medium. And in terms of me speaking, you are able to hear me if you are in this room. So simply because there is a medium, which is air. Okay, that means the sound is able to move through a medium called air, but not in a vacuum. Okay, in fact, you will even die in a vacuum because there's just nothing. There's no oxygen. There's nothing. It's an empty space with absolutely nothing. Okay, so we continue to say sound travel faster in solids than in liquids. Okay, so, and faster in liquids than in gases, right? So why then do that happen? Why does that happen? It's because the density of solids is higher than that of liquids. Okay, which means that the particles are closer in a solid as compared to liquids. Okay, so as the particles go closer to each other, sound is able to travel faster. Okay, but if we were to compare liquids and gases, the sound will travel faster in liquids as compared to what? As compared to gases. Why? Because the particles that make up a liquid are closer in comparison with the gases. Okay, so the density of water or rather any other liquid is higher than that of what? Of any other gas. Okay, so sound can be transmitted more easily in terms of that. Now that we know in which medium sound prefers, or rather is able to move faster in, now let's speak in terms of the speed of the medium. Okay, so the speed of the sound in a specific medium, sorry. So the speed of the sound depends on the medium the sound is traveling in. Okay, obviously we've spoken about that sound moves faster and further in a solid as compared to the liquids, and more faster in liquids as compared to gases. Okay, but what are the factors that affect the speed of sound? Okay, we do find in the second point is that the speed of sound also depends on the temperature of the medium. The hotter the medium, the faster the particles will move. Okay, so for example, let's make take a medium of what? A liquid medium. You know, let's look at just the particles that make up that medium. Okay, so that we can tell if the particles have an increased temperature or not. All right, so the faster the particles they will move, and therefore the quicker the sound will able to travel if the particles are moving faster. Okay, so we'll want the medium to be hotter because now the hotness of the medium will increase the average kinetic energy of the particles that makes up the medium, and therefore the sound will be able to travel faster and further. Now, that is why on the third bullet we had to mention that as we heat the substance, the particles of the substance have more kinetic energy and will vibrate faster and move faster. So sound can therefore be transmitted more easily and quickly in hotter substances. All right, so sound waves are pressure waves. That's one thing also we need to take note of. Okay, they are pressure waves. That is why they need the particles to be closer to each other, that of a medium, for them to travel faster. Hence, we prefer the solid substances or material, okay, because they are pressure waves. The speed of sound will therefore be influenced by the pressure of the medium through which it is traveling in. Okay, so we make a typical example of a sea level right in the deep part of the sea. Okay, so there's more pressure there as you compare to the higher up the mountain or at the surface of the sea. Okay, so at the sea level the pressure is higher than high top of the mountain. Okay, so that means that the sound will travel faster in the sea level as compared to higher up the mountains or high above the sea level. All right, then we had now to compare, because we're speaking in terms of the speed of sound in different mediums. All right, so then now we have to compare and say, okay, because now it's different, and we cannot be given a solid substance all the time. Even if it's a solid substance, it differs whether it is hotter, because when it's hotter, that means that the particles that make up the medium will then vibrate, having a higher average kinetic energy as compared to the ones that are not hotter or cold. We're comparing hot and cold. Okay, so still the speed of the sound in that same medium will not be the same because of what? Of the temperature being affected that affects the speed of sound. All right, so let's compare it against different mediums. In aluminium, it is approximately 6,420. In the brick, it is a different one, which is a 3,650. Copper, glass, gold, lead, water in the sea, air at 0 degrees Celsius, and air at 20 degrees Celsius. Okay, so you can see just a clear difference there. Air at 0 degrees Celsius, that means that it is cold. Okay, so it's sitting at 331 meters per second. All right, as compared to the air at 20 degrees Celsius, it's hot. All right, so that means the speed of sound will travel faster. That is why it's 343 meters per second. All right, then we speak in terms of an echo. An echo still falls under sound waves. Reflection, because that's what happens. The source is creating the sound. Okay, it's you go on top of the hill or a mountain or an empty space, a hall, okay, and then you clap your hands. And then few minutes later, all right, you hear that clap being reflected back into your ears. What happened? Let's explain it in detail. So that is the reflection of the sound waves. You created that clap. It went to hit the walls of the hall, and then a few seconds later, it came back into your ear. Okay, so that's an echo. So that is when you make a loud noise in a hall, you are likely to hear a voice again in a few seconds. Okay, so what is an echo in simple terms, you ask yourself? It's just reflection of sound waves. So they have to go, when something is being reflected, it means that it has bounced off, okay, and is coming back to its original direction. Okay, so this is a nice diagrammatic representation of an echo. Okay, because now here is this tiny human being. Okay, not a human being per se, it's a cartoon. So here's this tiny cartoon, it's clapping. Okay, so the sound is emitted, okay, from the source, from this cartoon, and it goes and hits the wall, and then a few seconds later, this cartoon is able to hear the sound that he made. All right, so that is an echo, and it's due to an empty space. Once now the sound is able to reach or bounce into a certain object, then it is able to get reflected back into your ears. However, that means that the sound had traveled twice the distance. If it means that from this point to that point, the distance was 2 meters, that means the sound have traveled this distance again in that direction. Okay. Also, when the sound wave collide with an object, they are reflected. Okay, you think of an individual particles that are oscillating in equilibrium position, colliding when the object wave they pass by. All right, so they bounce off. Okay, that's what reflection is. It's just the bouncing off of those sound waves back to the source. Right. So we also had to mention that in a space with many small objects, so you've got a chair, you've got a table, you've got a plate, you know, it's a space that is busy. It has many objects in it. Okay, so there are reflections. Okay, but the echo will not be as audible as when there's an empty hole in it. You know why? Because now this sound is being reflected in all these objects that are inside the room that you are in. Okay, so they are too small and they get too mixed up, and then you have an outcome that is very small for a human ear to hear. Okay, so that is why it's like, okay, there's a bouncing of this sound in all the objects inside the room. All right. However, if there is an open space, okay, would have lots of services. For example, school hall is empty, and then this reflected sound can also be heard louder, okay, because the sound will have to wait to be hit into the wall before coming back to the source. All right. Now, sound waves can also be used in ships. Sonar, sound and navigation ranging. Now, ships on the ocean make use of the reflecting properties of the sound waves to determine the depth of the ocean. All right, but how do they do that? Okay, so they emit the sound towards down, okay, on the ocean. All right, a sound wave is transmitted and bounces off the seabed right at the bottom of the sea. Then it bounces off, and then because the speed of sound is known, okay, the time lapse between the sending and the receiving of the sound can be measured, okay, from when you are sending or emitting the sound, okay, on the seabed. Then you start counting. Okay, that means that the time lapsing between the sending and receiving of the sound back, and also we can measure the distance from the ship to the bottom of the ocean, can be determined. Okay, so all of that, we call it sonar. It's an acronym, sorry, for sound navigation and ranging. Okay, because we use it so that we know the distance. Okay, we are able to tell the distance between where the source is being emitted to the bottom of the sea, because there are other factors that we are able to determine. All right, for example, we are able to tell the time that is lapsing, we are able to tell the distance, but now we can also now tell the speed of sound, okay, because of the other variables that we know. Okay, not only can we use that in ships, okay, but dolphins, which are animals that reside in the sea, can also be able to use the sound waves. In fact, they do use the sound waves, okay, in their daily living, okay, to maneuver, to be able to look for food, to be able to tell if there is an object that is approaching them, okay, and stuff like that. So we say animals like dolphins and bats, okay, make use of the sound waves to find their way, okay, inside the sea. Just like in ships on the ocean, bats use the sonar to navigate. Okay, how do they use that? They send, okay, a sound, a squeaky sound, as you may have heard them, okay, so it means that the waves that are sent out are reflected to an object that is approaching them or towards them or in the side, okay, around the animal, which is the dolphin in this case. So you find that the adult and the dolphin, the bats and the dolphins, okay, then use the reflected sound to form a picture, okay, of their surroundings. It can tell from the reflected sound, the sound that has went out from it, the squeaky sound that has went out from it, it has bounced from an object that is surrounding them, and then determining back to them being reflected sound, they can tell how far is this object, as it is the distance between the dolphin and the nearby object. Okay, it can tell also its shape as well as its size. So we say this whole way of navigating using sound waves, we refer to it as echolocation. Okay, so this is a nice diagrammatic representation so that we show you that this is a dolphin emitting, okay, a specific sound, And from that sound, it can tell, okay, there's a small fish that is approaching me, okay, in this direction, all right, depending on the reflection of sound. In which direction did the sound become reflected on? If it's this direction, that means this fish is in this direction, okay? So we call it echolocation because it uses echo to locate its surroundings, okay, to form a picture about its own surroundings, okay? Also, we had now today to look at the now frequency of a sound wave. Yes, we did look at the relationship between the frequency and the wavelength. Okay, we said the higher the frequency, the shorter the wavelength. Okay, so the frequency of the sound waves is what you is what your ear understand as what? As the pitch. Okay, so what is the pitch? I know pitch is just the new term that you're learning today. So the frequency of a wave is an objective quantity that can be measured, while the pitch refers to how different the frequencies are perceived by a human ear. Okay, so the relationship in simple terms between the frequency and the pitch, the higher, as you increase the frequency, okay, you then increase what? The pitch. Okay, as you decrease the frequency, you also decreasing what? The pitch. So that means the frequency is directly proportional to the what? To the pitch. Now, in the diagrams that are portrayed in here, you've got a low frequency at the top. So this is a diagram with a low frequency. And this one has got a high frequency. Right. And how can we tell that? Because now a frequency is the number of waves passing through a certain point in 1 second. Okay. So if we were to count in here, there's just 1, 2, and 3. All right. But when you look at the diagram at the bottom, okay, so it's 1, 2, 3, 4, 5, 6, 7, 8. Okay, so the number of waves in the bottom diagram, there's 8 waves. Okay, so that is why it has a higher frequency. And because we had said there's a direct proportional relationship between frequency and pitch, so that means the lower the frequency, the lower the pitch. Okay, and then the higher the frequency, the higher the pitch. That's how related these two are. Okay, so from this diagram, then we can tell that, okay, because the first diagram has got a lower frequency, it has a low pitch. Even before you can even look at here, so that you are able to analyze your diagram successfully. Also, let's look at now the relationship between amplitude of the sound wave and loudness. Okay, so amplitude of the sound wave is then, well, it rather determines the loudness or volume. Okay, is it loud or is it soft? You look at the amplitude of the sound wave. All right, so let's look at the sound wave. Let's just assume this one is a 1 here. So this point in here is 1. Okay, so anything above that, it's going to be approaching 2. Right, so this being our starting point, 0. Okay, so that means the amplitude, assuming that this is given in meters, so assuming that this is not given in meters, that means that the amplitude for a sound wave B, okay, is what? Is 2 meters. Sorry, why am I saying 2 meters? It's 1 meter. Okay, and then when we look at the sound wave C, it is above 1. Okay, so we can give it a 1,5 meter. Okay, so now we know the amplitude of both these two sound waves. Okay, now let's determine now which one is louder and which one is softer. Okay, now before we even determine that, what is the relationship between amplitude and loudness? Okay, so the smaller the amplitude, the softer the sound. Okay, and then the higher the amplitude, the louder the sound. Okay, so that means between these two diagrams, or between these two sound waves, B has got a smaller amplitude as compared to what? To C. What does that tell us? This one is soft and this one is louder. What informed that is the amplitude, because the amplitude is what? It is longer. In this case, it is shorter, because we're talking in terms of a displacement, a maximum displacement from the rest position. That is the definition of what an amplitude is. Okay, so that means a larger amplitude means a loud sound. A larger amplitude, this is larger as compared to this one, okay, means a louder sound, and a small amplitude means a softer sound. That is how simple it is. All right, let's move right along. Let's look at now at the types of waves types of sound waves that they are, okay, with a wide range of frequencies. Okay, so we say the human ear can detect a wide range of frequencies. As humans, we are able to hear different frequencies with our ears, okay, ranging from 20 to 20,000 hertz. Okay, so that is an audible sound. Okay, audible sound waves range from a frequency of 20 to 20,000 hertz. Okay, that is what a human ear is able to hear, right? And then any sound with below the 20 hertz is known as infra, and any sound that is above the 20,000 hertz is known as ultra. So our interval really is that of what? So you have a 0 if you had to draw a number line, and then you have 20, and then you had 20,000. Okay, why am I writing my 20,000 like this? So it's 20,000. So this is a frequency in what? In hertz. Right. So this is the audible range. This is the audible range. Audible frequency. The one that humans are able to hear. Now, anything below that, below 20,000 hertz, 20 hertz below that 20 hertz, then it's an infra sound. And anything above 20,000 is an ultra sound. Right. Now, ultrasound waves have a frequency above the normal range. It's too high. Our ears will just bust. Will not be able to hear that. It's just too loud for our ears. And then the one that is infra is just too small. It's like you dropping a toilet paper on the floor. It's just too small for our ears to hear that. Okay, that is how simple it is. They can be used to scan. That is your what? Your ultrasound. So your ultrasound, because now it is too high for human ear to hear. It is bad, okay, for us to hear it. However, it is not all bad. That means that we are able to use it on other things. Okay, for example, we are able to scan the fetus, which is a baby during pregnancy. We are able to monitor the heartbeats of a fetus as well, so that we give a birth to healthy babies. It is able to detect in the manufactured for the manufacturing equipment as well. We're able to monitor and examine the gallbladders, the kidneys. We are able to examine the blood flow. We are able to examine a lot of things using the ultrasound. So in the medical world, in the medical field, the ultrasound it is used so perfectly for all of those purposes. All right. So this is a table that is showing us the hearing ranges of some common animals as compared to humans. Okay, because with humans we already know that they are able to hear between 20 to 20,000 hertz. Okay, so dogs can hear 50 to between 50 to 45,000, and then cats 45 to 85,000 hertz, and then bats 20 hertz to 120,000 hertz. Okay, and then dolphins 0.25, from as low as 0.25 hertz to 200,000, mainly because they use sound waves for their everyday living, to just sense what is around them, for detection of food. So they use them every day. So elephants as low as 5 to what? To 10,000 hertz. Okay. So we've spoken about the uses of sound waves, okay, in our everyday lives. Okay, in the medical world, we examine the blood flow, we examine the gallbladders, the kidneys, we examine the fetus. We are able to detect the heartbeats of the fetus so that we can tell whether the baby is growing perfectly fine or not. Are there any abnormalities? We can even pick them up way before babies are born. All right. So in the medical world, ultrasounds are just used nicely. Okay. So that is the part of the sound waves I wanted us to talk about. Now, let's apply all what we've learned today on sound waves and on the previous lesson, terminology-wise, okay, so that we learn how to best answer, okay, these questions, okay. May I please have my calculator with me before I begin on this one, because I'm going to need my calculator. So, before they give me my calculator, let's analyze the question. Remember, it is very important to analyze the question all the time. Okay, so question 7, read your statement, take your time, go through your diagram all the time, analyze what is it that is given to you. Okay, what information is given to you? Thank you so much. What information is given to you, so that you are able to use what is given to you to find out what question is being brought to you or to your attention. Okay, so this is just question 7, taken from previous question papers, all right, which is 7.1. It says the diagram below shows the pattern obtained for a sound wave with a frequency of 500 hertz. Okay, because in that statement that is given to you, you get some of the variables that are just given in numbers as well. So this means that I do know that I have this pattern of a sound wave, and it has a frequency of what? Of 500 hertz. You look at the SI unit in which it is given into. Okay, so if it's in the correct, you know now that a frequency needs to be in SI units of hertz. Okay, so once it is not in hertz, you have to fix it. If it's in kilohertz, fix it. Okay, somebody can say, but then how can kilo means 1,000. So you're moving from kilo, you're going to what? To hertz. That means you have to do what? To multiply by 1,000. Okay, so, and then you look at this diagrammatic representation as well. Is it, the other question that you ask yourself, is it a longitudinal wave or is it a transverse wave? So the question of saying, is it a pulse or is it a wave, is out, because I can see a continuous disturbance in here. That means it is a wave. Okay, so because now there's a continuous disturbance and not just a single disturbance, it is a wave, but it's just a matter now of finding out, is this a transverse wave or is this a longitudinal wave? You remind yourself of the definitions of each of these types of wave. You said, okay, with the transverse wave, the particles of the medium vibrate at the right angle to the direction of the propagation of the wave. Okay, so it's not the case in this time. Okay, and then with the longitudinal wave, the particles of the medium, they're vibrating parallel to the direction of the propagation of the wave. You're like, gotcha. Because we had also mentioned that longitudinal wave can be represented by what? By the lines. Okay, so this is a longitudinal wave. Right. Then I'm writing what I'm seeing and I'm given. All right, so this is frequency it is 500 hertz, and I'm writing it down so that I don't forget it. Right, and then you look at the distance that is given. Remember, this cannot be a wavelength, and reason for that, we said a definition of a wavelength is the distance between two successive, in terms of a longitudinal, it has to be two successive compressions or two successive refractions. But in this case, it's a distance from here to there. So that means it has jumped a compression. Successive means this one and then the next one, then the next one. Okay, so that means this one, there's a compression, there's a refraction, there's a compression, there's a refraction, there's a compression. Okay, so we need then to divide it by what? Because it's giving us how many waves. You need to start counting now. So there's 1, there is 2 full waves. So that means that this 1,6 needs to be divided by what? By 2, so that it gives you what? A 0,8 meters. If it was a transverse wave, it would have had, the wavelength would have had to be what? The distance between the two successive crests, or the distance between the two successive trough. Okay? So in this case, it's a compression, it's a refraction, then it's one wave. It's a compression, it's a refraction, it's wave number 2. It's a compression, and then it's incomplete. Hence, I had to divide it by what? By 2. Because how many full waves are there? There are 2 full waves. So therefore, wavelength is equals to 0,8 meters. Okay? Because what is given there is just a distance. Okay? So I'm adding it here to the data that I am collecting. Okay? So it means that my wavelength is 0,8 meters. All right? Now let's attempt the question. So please give yourself time to go through the statement that is given to you, analyze the diagram properly, write down what is it that is given to you, then attack. Let's attack now. Okay, so I'm going to start by writing my data so that I don't forget it. We have a frequency of what? Of 500 hertz, and then I have a wavelength of 0,8 meters. Right, so they're saying define the term frequency of the wave. What is frequency of the wave? It is number of waves that pass through a certain point in 1 second. Please define fully. Is the number of waves that pass through a certain point in 1 second. Two ticks. Okay, even if you said it's the number of waves per second in 1 second, that is correct. 2 marks or nothing. You define fully, 2 full marks. You leave certain keywords, nothing. 7.1.2, write down the letters that represent 2 consecutive points on the what? On the wave which are in phase. Okay, let's underline in phase. All right, which points then are showing the in phase? Let's look at this diagram. All right, so remember with in phase, we said that it is the points that are in the same state of vibration. Okay, so my A, I'm gonna circle it so that it's easier to see, and my C are in the same state of vibration because they are in refractions. My B, I'm putting it because that was my first set of P, and then my B as well as my D is in phase with each other. So that means B is in phase with D. Someone else can come and say, as well as D and F, you can continue with those combination. Okay, so 2 points that are in phase AC and BD. AC, BD. A and C, okay? So we just, because it's now 2 consecutive points, another person can say B and D. Okay, so that's what I meant when you say with this kind of questioning, please don't say B. Okay, B, you're comparing it with what? Okay, D, you're not comparing it with anything. Okay, because we need the what, the pair, because you're saying these are 2 points, okay, that are in phase. Okay, and then name the section that is labeled A. I'm just gonna go quickly back. A, can you see where A is at? So that means the lines are far apart from each other, right? And with B, the lines are closer to each other. We said this, we refer to a rarefaction, and then we refer to the other one as the, so this one is a what? Is a rarefaction. Okay, for 1 mark. Then we had to calculate the speed of the wave. You're like, oh, okay, I am given, I have my data right here. So we're going to choose a proper formula, okay, so that we substitute correctly and then give our answer with correct SI unit. So we can just say, just for space, V is equals to frequency times lambda. All right. And then because we're trying to calculate the speed, already it is in the subject of the formula. Even if it wasn't, just use the formula as it is, because as you try sometimes to maneuver the formula, you just get it wrong. Meaning that you just recreate your own formula that doesn't exist. And then you lose marks, because copying the formula from the formula sheet, it just gives you a mark. Okay. So 500 multiplied by 0.8. And I'm able to substitute these numbers because they came in incorrect SI unit. So your 500 multiplied by 0.8 is giving us what? 400. And you ask yourself that, oh, I was calculating speed. Right. So it has to be in what? Meters per second. All right. Moving right along, still using the same data. Okay. Now we said the amplitude is increased. Okay. It is now, the amplitude is what? It is increased. You stop. Go through your head again and say, okay, what is it that is affected by amplitude? It is the loudness. Okay. What is it that is affected by the frequency? It is the pitch of the sound wave. All right. So when the statement then says the amplitude is increased while the frequency remained the same, this is very important. While the frequency remained the same, amplitude reminds you of what? Of loudness. Frequency reminds you of what? Of the pitch. And these just have a direct proportionality relationship. Okay. How will this affect each of the following? Okay, we have to write only increase, decrease, or remain the same. How will it affect the pitch? Already through your analysis of the question, as you are reading it, okay, you already had wrote your answers. So the pitch, because now the frequency is remaining the same, that means the pitch will also do what? Remain the same. Right? And then how will this change affect each of the following? Now we're talking in terms of loudness. How will loudness be affected by this change? Okay, loudness it has a relationship with amplitude. So because amplitude is being increased, okay, loudness will also do what? Increase. So it will also be increased. Okay. That is how simple it is to look at these questions, okay? Because today we're just exploring the sound waves, all right? 7.3, they're saying, in an experiment, a learner wants to determine the speed of sound in air. The learner wants to do what? To determine the speed of sound in air, all right? So what does he do? He stands 136 meters away from a wall. Okay, so here is the student or learner 136 meters away from a wall. Okay, claps his hands and listens to the echo. All right, so he hears the echo 0.8 seconds. Okay, let me just stop there. Let's read again. In an experiment, a learner wants to determine the speed of sound in the air. He stands 136 meters away from a certain ball, okay, and then claps his hands and listens to the echo. He hears the echo 0.6 seconds, okay, after 0.8 seconds. Why do I keep saying 0.6? 0.8 seconds. Use this information to calculate the speed of sound in air. Now let's do something there. Let's just collect data and put it in once. So here's my data. Okay, so the distance is 136 meters away from the wall. But now, because we're talking about the distance that is being traveled by the sound wave, that means the sound wave was being emitted by the learner towards the wall, okay, and then the sound wave moved back to the what? To the learner, so that the learner is able to do what? To hear the reflection of the sound, or rather the echo. Okay, so that means the distance that is being traveled by the sound wave is twice the original distance. So that means it's 136 times 2. 136 meters going, and then 136 coming back to the learner. Okay, so we say 136 multiplied by 2 is going to give us a distance of what? Of 272 meters. This is the distance that is traveled by the sound wave, right? And then the time it took for this sound wave to be head back, okay, or to be reflected back was what? 0.8 seconds. All right, and then in the question says determine the speed of sound in the air. Okay, so that means we're going to use this to calculate what? To calculate the speed of sound in air. So based on what I'm given, I want the speed. Okay, so I can use this formula and say dt, right? Because I want the speed, that means it's going to be distance divided by time. So we say speed is equal to distance over time. All right, so distance is what? 272 meters divided by the time is 0.8 seconds. Okay, so with your substitution, it's not important that you put the SI unit, but your answer, there has to be a correct SI unit. So this is 272 divided by 0.8, which then gives us a 340 meters per second, which is speed. Nicely done. So another way of just sorting out what the information that is given to you, please write your data and then look at it, analyze it. Is it incorrect SI unit or not? If it's not, start doing your conversion first, okay, before you even attempt to say, okay, let me think about the formula, let me think about the substitution, and so on. Okay, 7.4, we're still on question number 7. Ultrasound has many technological uses in the medical and other applications. Okay, so we have to determine the term ultrasound. It is the sound with frequency of higher than what? Or rather greater than 20,000 hertz. Okay, so it is the sound with frequency greater than 20,000 hertz. Okay, because it's ultra. Then 7.4.2 says name 3 uses of ultrasound in the medical field. Okay, so we want to detect the heartbeat of the fetus, we want to examine the kidneys, the gallstones, or the kidneys. We want to examine the blood flow. We want to examine tumors for people with cancer. Tumors. Okay, so we can use the ultrasound in the medical field for all these different reasons. Okay, you just write the ones that, because they had said 3, any 3. Okay, for 19 marks, easy. Okay, so this is a different question paper again. Still we're exploring the sound waves. Okay, it says a flute produces a sound wave with a frequency of 360 hertz. Nazia, 360 hertz, that is my frequency. You write it down. You say, okay, let me collect my data. 360 hertz. I don't need to convert anything. It is the frequency. It's supposed to be in hertz. Accept that the speed of sound at that point is 325 meters per second. Okay. So my V is 325 meters per second. Right. Now let's explore the questions. So on this page, I'm going to write my data again. So we had 360 hertz for frequency. And then for the speed of sound, we had 325 meters per second. Right, let's get down with the questions. Right, to say question 6.1. For this sound wave, calculate the period, give your answer in scientific notation. Now we need to calculate the period, right? We say T is equals to 1 over frequency, okay? 1 over frequency. You already know your frequency. It's 360. Why does this look like a 5? 60, okay? So this is going to be 1 over 360. So this is going to be what? 1 divided by 360 is giving us 2,78 times 10 to the power of -3. Because it is period, we write seconds. Okay? Easy. For 6.1.2, the wavelength. Okay? So we have to calculate the wavelength of the sound wave. Okay, so looking at our data, okay, we can be able to find the wavelength by simply saying V is equals to frequency multiplied by lambda, lambda being the wavelength, and then we do have 325 as the speed of the sound wave is equals to 360 as the frequency of the sound wave in hertz, and then multiply by lambda, which is what we are looking for, divided by 360 divided by 360. So this 360 cancels that one, and then lambda is what? Wavelength is 325 divided by 360. That is going to be 0.90. Therefore, okay, I'm just going to write it here. Therefore, lambda is equals to 0.90 meters. Okay. Formula substitution answer. 6.2. A string of a guitar oscillates at a period of 0.005 seconds. Okay, so because now this is no longer 6.1, I'm starting onto a new question, still under question 6. So this is my period, which is 0, so if I were to write my data, I will say my T, capital letter T, 0.005 seconds. The speed of sound in air is 343 meters per second. 343 meters per second. Okay, so I'm just given two variables. There's just a guitar. Okay, Before I even start on this page, let's write my data. I have a period of what? Of 0,005 seconds, and I've got my speed of sound in air, which is 343 meters per second. Okay, yes. And then 6.2.1, are sound waves longitudinal or transverse wave? Definitely longitudinal. Definitely longitudinal. Okay, longitudinal waves. Okay, 6.2.2, calculate the frequency of the strings oscillations. Calculate the frequency of the strings oscillations. Formula for the frequency that we can use. Okay, in this case, looking at our data, we can use frequency is equals to 1 over period, which is going to be 1 over my period is 0,005, and then 1 divided by 0,005 is giving us 200. And because we are calculating the frequency, is going to be 200 hertz. Right. Moving right along, calculate the wavelength of the sound wave produced by the string. Okay. Calculate the what? The wavelength. Okay. I can do that. We can do that because we're doing it together. Now, I'm just going to move it up a bit because my space is less. Let's just say V is equals to frequency multiplied by lambda, and I have a 343 is equals to my frequency of what? Of 200, and the wavelength is unknown. Okay, all right. Did we substitute right? That is beautiful. Divide by 200, divide by 200. I'm going to take it up a bit. So this cancels that. So that lambda is equals to 343 divided by 200. And it's giving us a 1,715 meters. Someone else can even derive it and say it's going to be approximately 1,2 meters. Okay, well, this which is no 1,72 meters, but just rather leave it as 1,715. Okay, moving right along, the frequency of the string increases. Okay, how will this affect the pitch of the sound? Okay, the frequency of the string increases. How will this affect the pitch of the sound? Remember the relationship between the two. We have to say write down only increase, decrease, or remain the same. So that means that if the frequency is increasing, the pitch will also do what? Increase. Okay, 6.2.5. How does the increased frequency mentioned in question 6.2.4, all right, influence loudness of the string sound? The frequency, there is no relationship between frequency and loudness. Okay, so it will do what? It will remain the same, because there's a relationship between amplitude and loudness, frequency and pitch. Okay. Also, we had to write down increase, decrease, or remain the same. Hence, we wrote remain the same. Okay. 6.3, give 2 applications of ultrasound in everyday life. Whoa. Ultrasound, the one that has a higher frequency, the greater than 200 hertz. Okay, 200,000 hertz, that is. So we examining tutors tumor, because now we said 2, we are able to detect heartbeat of a fetus. Okay, as simple as that. For all 17 marks. 17 marks, that's how easy it is to get all the 17 marks. Okay, so don't sleep on these marks. Okay, so you and I have done linear activity 1 and we've done linear activity 2. So I'm thinking, are you thinking what I'm thinking? I'm thinking that linear activity 3 is done by you individually at home, so that you get the feel whether you did understand what we spoke about today or you didn't. Okay, do it and then we'll get the answers together when we meet again. So it says question 7, starting on the new page, the speed of sound in the same substance X in the 3 different phases of X are given in the table below. Okay, so we are not told what medium it is, so it's just given as X. Okay, and then remember, always read the statement that is given to you, always analyze the diagrams that are given to you before you even attempt to answer the questions. All right, so there's a table in this case. So it says the speed of sound in meters per second in different phases of X. Okay, which speed was measured when X was in gas phase? Remember when we spoke about the speed of sound in different mediums? Okay, we said that sound is able to travel faster in what? In solid as compared to liquids, and faster in liquids as compared to the gases. So judging by the values that are given here, the values of the speed, okay, then you are able to tell which one is in the gas phase, which one is in the solid phase, by just looking at the data that is given to us. Okay. 7.2, the captain of the ship wants to find the depth of the sea by using sonar. Okay, and an ultrasonic sound of frequency of 32 kilohertz. Kilo means 1,000. So in short, that is just plainly 32,000 is produced, and the greater that is reflected by and the sound is reflected by the sea floor is received at 0.25 seconds later. All right, so the wavelength of the sound signal is from 0.05 meters. Write your data, do your conversions, then begin answering. Okay, 7.2.1 goes on to say, what is the name given, okay, to the reflected sound? That sound that you hear after a certain period of time, certain few seconds. What name do we give it? Yeah, we spoke about it. 7.2.2, calculate the depth of the sea. Oh, the depth of the sea, the distance of from where the sound is being produced to the seabed. What is the depth of the sea? Okay. 7.3, the loudness and pitch are two important characteristics of sound. Two waveforms, P and Q, obtained in an oscilloscope and was shown in the diagram below. So we've got wavefront P and we've got wavefront Q. Study the diagrams. Study what is on the x-axis, what is on the y-axis, how is the waveform P different from waveform Q, because believe in me, all the questions that are following are going to be resting on that. 7.3.1, which one of the waveforms, waveform P and waveform Q, will produce a louder sound? What determines the loudness? The amplitude. So you had to go back, look which one has a higher amplitude as compared to the other one. Okay, 7.3.2 goes on to say, write down the relationship between pitch and frequency. That's all we've been talking about this entire lesson. 7.4, ultrasonic, audible, and infrasound are three different types of sound under three ranges of frequency. They are just telling us that, and I know you already know that. 7.4.1 is where the question is at. What is meant by ultrasonic? Ultra, infra, audible. Okay. 7.4.2, write down the frequency range of audible sound, the one that human ears are able to hear. 21 marks, the total mark is. Okay, I know it is very simple. I know you're going to be great at doing it. Attempt it. Attempt it, because you deserve that greatness. That is why Benjamin Franklin said, an education is the investment with greatest returns. You need those returns. But how can you know if you're not investing? You're not going to get rewarded with anything. Those returns are not going to be as great. So hence we say education is the investment with the greatest returns. We have to begin now to start investing so that we can have greatest returns. I hope you had a fun time with me. I really do, because I did had a fun time with you. But I hope you did understand all the concepts, all the formulas, how we should substitute, how we should do conversions, and how we should write our answers with SI units. Okay, hope to see you next time. Goodbye.